AI is not just a buzzword, it's a revolution, and at its core, neural networks. The brain like structures turning science fiction into reality. Besides the fancy tasks of generating images and making robots highly functional, neural networks are just function approximators. But how do neural networks look and why do they work so well? To understand it, let's start with a toy example. Think of the game in which people are lined up at a good distance from each other, and the task is to spread a message from one end to the other. Since they are far, some information is lost. The person on the last tells their answer to a machine that states the rightness of the message, and the last person starts confirming with the second last person, and so on. This forward and backward passing of messages keeps on happening till the last person actually knows the right message. Now, replace the people with nodes and the message passing with edges. You get your look of a neural network. Also stacks some stuff vertically for an actual feel. In simple terms, think of a neural network like a mini brain made of nodes and edges. Nodes hold information and edges control how much of this information moves around in the network. In basic type of neural network, known as a multi-layer perceptron, these nodes can be turned on, that is, activated, or turned off, non-activated. We turn these nodes by using special functions called activation functions. Mathematically, we can use these functions because it lets the neural network handle more complex patterns. Imagine a fairly simple network. It has one input node connected to one output node with something called a trainable edge. This edge has a weight like a number w, which changes the value from the input node before passing it to the output node. However, the output node doesn't store this value right away. Instead, it uses an activation function to decide what to do with it. If the value is bigger than 1, the function keeps it the same, else it turns it to 0. This is an example of a popular activation function called ReLU. And do not forget, we need a mechanism at the end to gauge the distance between the model's output and the actual answer, aka the error. Here, we can just use a squared error to get the error. The square error here helps in ensuring that equal negative and positive errors are treated equally, and also some other reasons. The main goal here is to find the best weight for this edge, aka the weight W, so the network can correctly understand the relationship between the given inputs and outputs. At the beginning, we pick this weight randomly, but in a smart way, not like completely random. A video on that some other day. Let me pick an example in which we will try to fit the network for the input-output pairs. Setting the weight randomly as 0.1, the neural network resembles the function ReLU of input times the weight. Taking the first input pair and the input 2, the output comes out as 0.2. Damn, that's far from our actual answer of 19.6, resulting in an error of almost 370. Now what? How do we change the weight such that the output for input 2 is close to 19.6? The answer lies in a simple calculus rule, gradient descent. To understand that, look at the following arbitrary curve of error versus the weight. You can get the minimum by various methods, taking the derivative and equating it to 0, or Newton's second order optimization technique. Alas, these all are computationally intense. Therefore, we use gradient descent. I hope you know that the slope of a curve gives the direction of the steepest descent, as shown here. If the tangent at the given weight has a positive slope, then the weight needs to be decreased. On the other hand, if the slope is negative, guess what? The weight needs to be increased. In order to reach the closest minimum, this jumping of iterative weights is the gradient descent. It yields quite a simple yet satisfying rule. If the slope is negative, negative times negative is positive, hence the new weight is bigger than the old and vice versa. There's one more catch. Slope is the tangent of the angle that the line makes with the positive x-axis, and this value can be from negative infinity to positive, resulting in humongous jumps. To prevent it, we multiply the slope with a small number, almost always less than 1, the learning rate, giving you this new formula. Wow, It is finally time to apply and visualize the working of this simple network. I have written a fairly simple Python function for forward pass, in which for all inputs and the given weight W, it calculates the output based on the predefined network. And here you can see the backward method calculating the slope of the error with respect to the weight. In the second last line, I am aggregating all the gradients for various inputs in order to update the single weight W. Finally, using the update rule 10 times and a learning rate of 0.1, let the magic happen. Time to see the results. The model stopped with the weight being almost 9.8. Wow, we just found the acceleration due to gravity of the F is equal to mg relation. Last thing, since I already knew the input-output relation, you could also see the various models that our mini neural network came up with and their distance from the actual model. And yeah, it works. To end the video, I would like you to know that a single layer with an activation is quite powerful too. As the data and complexity increased, a lot of smart algorithms need to exist. Convolutions for both images and time data, recurrent attention and transformer structure for large text. ChatGPT is a part of transformer network, by the way. And autoencoders for generative AI systems. But a general intuition and a sense of visualization gets lost behind these cumbersome mathematical equations. And this video is my first step to uncover these limitations. Thank you for watching. See you soon.